Welcome to Study Loop.
All right, hello there. So today we're going to be talking about how to draw the Lewis structures of important resonance forms of these two compounds here. So we'll begin with the molecular nitrogen here, or this nitrogen ion, N3 ion, which is basically just three nitrogens bonded to each other. And the way we do that is like with any other Lewis structure problem, we draw our molecular arrangement of the three atoms, right, as so. And of course, it's not an actual 3D structure, but just the bonding relationships can be shown here. So we have the three nitrogens written. We can draw a single bond in between the central nitrogen and the two nitrogens on the side. Then we'll calculate the valence electrons. So we know that each nitrogen has 5 times 3 of them gives us 15, plus we have a negative charge. So we have, and this comes from negative charge, and we have a total of 16 valence electrons, right? So we have 4 accounted for right here with the single bonds. The rest we will fill in with lone pairs. So we have, since there are 4 here, we need 12 in lone pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're all set with a total number of electrons. The problem is that, and you may have noticed this already, in that our middle N does not have our octet. So in order to fill the octet for the central N, we need to move a lone pair from either of the peripheral ends, actually both of them, and also should put the negative charge here, in order to form double bonds. So we move the lone pairs to form double bonds in order for our central N to have a full octet, and which we will, because each line represents 2 electrons, 2, 4, 6, 8, and we're just missing one lone pair here. But now everything has an octet, everything has the right number of electrons, and we are set with our 16. So this is definitely an important resonance form here, and this is actually not because of the fact that our central N does not have an octet. So this is definitely an important form. Now, because we have 3 equivalent ends bonded to each other, we can transition to other important forms by just moving one of the lone pairs into a double, to form a triple bond, and on the other side, to compensate for the fact that we'd be adding a triple bond here, we need to, in order to not overload the octet of the central N, we need to compensate and move one of these pi bonds, one of these double bonds, back to a lone pair. So we can do that here. So we'll do that, and we'll do this, and that will give us this structure. So that the electrons from the double bond are now a lone pair here, back to a single bond, and then we have a triple bond here because we've moved these electrons into the triple bond, and we're left with one lone pair here. So that's definitely another important form as well. You may also notice that there's no necessity as to why I put the triple bond here and the single bond here, and that in fact gives us our other form where we can just flip where the triple bond is and where the single bond is. So this structure right here is another important form. And I did not show the electron pushing between these two because all it is just flipping, and it's the same situation. So 2 lone pairs from here would come back, 1 lone pair would go over here. Actually, you would more likely transition between this form and this form here. But you can transition from this to this, but more likely than not, it would be easier to just go the other way from here. And yeah, that's how, so these 3 structures are your most important resonance forms, and that's how you would address that. So for this next part, NO2 minus, once again, we start by drawing our central atom first, which would be N because it is it has the lower group number. We can draw our 2 O's on either side. We'll draw a single bond in, we'll count the number of valence electrons. So we got 5 plus 2 times 6 is 12, plus the 1 from the negative charge gives us 18 valence electrons. So we can start filling those in. So we've already taken care of 4, so we need 14 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we have 2 more left over, so we'll put them here. Now, our N does not have a full octet, so we are going to need some double bonds. However, we will not need a double bond on either side. We would just need one of the oxygens to move, one of its lone pairs to form. And this is, of course, surrounded by a negative charge. And yes, so we will move one of these lone pairs to form a double bond. I'm just going to erase it in order to save some space. but we can move those lone pair electrons to form a double bond, like so. So this is one important resonance form. And once again, you may just notice that the other important resonance form is actually just the flip of this. And now we would have the double bond here, the single bond here. So it would look like this. So again, I did not show the actual electron pushing, but essentially what would happen is in order to go basically backwards, you would probably have to move these electrons back this way and these electrons to come over. So I'll just draw those in. So you would have this double bond coming back to form a lone pair and this lone pair coming back to form a double bond, and that's how you'd form